Donc, bienvenue à cette nouvelle cinquième séance du séminaire autour des structures de contrôle. So I will switch to English. So today we have the pleasure to welcome Matija Pretnar, who is professor at the University of Ljubljana in Slovenia. And so Matija was one of the pioneers in the field of algebraic effects and effect handlers. I think so. He did his PhD at Edinburgh, and I think he's doing this time working with Gordon Plotkin that they invented effect handlers first as a semantic device and then as a programming language construct. And since then, he and his colleague Andrei Bauer has been developing the F experimental programming language. So the first language with algebraic effects and handlers. And I'm extremely grateful to Matija for his tutorial paper that he wrote in 2015, which is really the paper that convinced me that there was something new and relevant and in the world of programming languages in those effect handlers. It was not just algebra for the sake of algebra. And I think his talk today will drive this point home. It is not just algebra for the sake of algebra. Thank you, Matija.
Thank you very much for this kind introduction and for the invitation. I'm really honored to be in this place, not only because it's so historic and beautiful, but for personal reasons. Because so maybe I should just start with the title, the mathematically inspired language constructs. So I never liked programming. So I saw C when I was in high school. It didn't convince me. So my only programming experience was in BASIC or in Logo when I was in the start of elementary school. And so I naturally enrolled into the Faculty of Mathematics and Physics, where I still work today. But then in the second year of my undergraduate studies, things changed. So Andrei Bauer came back from finishing his PhD at CMU, and he gave a series of talks. And in those talks, he introduced OCaml, okay? And I immediately fell in love. I became I can still recall the moment when he showed sum types and pattern matching to me, that I saw, this is the real thing. I want to study this for the rest of my life. And so I did for the next 20 years. So thank you, Xavier, for bringing this to me. So another thing I really like is the title of this seminar series. So it's not just control structures, but it is from goto to algebraic effects. And I don't like it because of algebraic effects. I like it because it shows an interval, how control structures have evolved over this span of 75 years. Okay? But I, as a mathematician, what I'm wondering is, in the next 75 years, so it will be just the end of this century, what would the title of that seminar series be then? We know where we are starting, but we don't know where we are going to finish. But one thing, we can be sure that whatever lies behind those question marks will have a mathematical background behind it, right? Because the ideas, function types, sum types, right? Those, we can see that they started a number of decades ago in mathematics, then theoretical computer science, and now they appear everywhere. There is almost no sane modern language without them. Okay? So we can be sure that things are going in that direction. Okay? So this will be sort of the overarching theme of my talk. Those programming constructs that are inspired from mathematics, because I believe that those are here to stay. Okay? So now let's change to the main theme of handlers. But it won't be the main theme because you've heard about handlers for last couple of weeks or so. So what I'm instead going to tell you about is 3 things. So first thing, the story behind effect handlers. So Xavier already sketched it briefly. I can tell you a bit of behind-the-scenes stories. And then I'm going to show you 2 ways how to go onwards from them. So you've covered effect systems today. So I'm going to show you how we can go from effect systems upwards towards mathematics or downwards towards real-world problems, right? The ones that we have to tackle right now, okay? And the differences between those 2 approaches. Okay, so let me first start with the history of handlers. So the mathematical understanding of effect systems, we could say that the main event that started this whole thing was Eugenio Moggi recognizing that monads lie behind notions of computations, as he called them. So various concepts were unified, and not only were they unified, they were unified by a pre-existing mathematical concept, right? If you find something that has existed in mathematics for 50 years or so, you know you're on the right track. Okay? So, but this was still mathematics, right? If you go through Moggi's original paper in the examples that you see that he's defining monads using mu, the multiplication. It's of course mathematically more simple, more elegant, but it's not what we use nowadays. He actually notices this in the introduction. He gives an alternative definition which is easier to justify computationally. Okay? And then in the subsequent papers, in the journal papers which came out just a couple of years after, he already switched to, well, not exactly to bind, which we use right now, but to lifting of monadic functions, which is just bind with order of arguments changed around. So we already see the slow change of moving from a mathematical concept into a useful construct. And then the next step came when Philip Wadler tried to implement monads in Haskell, right? Because Eugenio just wanted to give meaning to existing effects in a unified way. And I regret that I didn't ask Philip the last time I saw him, like where his start was, okay? But we know where he ended up with. So he translated mathematical notions into Haskell, which was powerful enough to support them. So he encoded unit and join as function. He still used join, but you can already again see the monadic bind lying in his comprehensions. Okay? But he did more than just translate things into Haskell. Putting things into Haskell allowed him to explore the horizon. And in there, he found examples which you previously wouldn't consider as a notion of computation, as something that is happening outside the computation. For example, parsers. Okay? So this is the point where monads became a control structure. Okay? So if you ask a Haskell programmer what is a monad, or anyone else, they will tell you a monad is given by 3 things: the type constructor, the unit, and the bind. Okay? But this is just half of the story. If you give those 3 things, you haven't told anything interesting yet. In order to express effects, you also need the second part, which are sources of effects. So for example, for non-deterministic choice, we have the example here. The constructor is the power set, the unit is embedding into the singleton, and the bind is a union over the results of the previous computation. But you still need sources of non-determinism. For example, a binary choice and a failure. Okay? Those you have to specify for each effect individually. Okay? And this is then what Gordon Plotkin and John Power sought to unify. Okay? And they did with algebraic effects. Okay? So they figured out that you don't need to start with the monadic operations and the effect-specific constructors. What you can do is you start with just defining a signature of operations and equations that satisfy them. Okay? And from those, you can generate a monad. How? You went through this already in this series, but let me just recap. So we know that from those two operations, you can build trees, which are branching on each non-deterministic choice. And you can represent a tree like this. So here we have a program which chooses between doing B, or again choosing between choosing A or C, or choosing B or fail. Okay? And now, because you have those equations, for example, you have associativity equation, you're free to reorder the parentheses. So we are converging towards a normal form. Okay? And because we have commutativity, we can reorder the terms inside those parentheses. And finally, because we have idempotency and the unit laws, we can coalesce two B's and get rid of fail. So we end up with a normal form which just lists all the elements present in the original tree, which is equivalent to the power set. Okay. So with this approach, Gordon Plotkin and John Power managed to express multiple monads. The exceptions monad, partially, the state monad, the choice monad, the IO monad, and the probability monad. So continuations escaped them, but another thing that escaped them was exception handling. So exception is given by exception monad needs to have an operation for raising exceptions and an operation for handling exceptions. Okay? And the latter one turned out not to be algebraic. So let's see why it's not algebraic. Okay? So let's say that we want it try to be algebraic. We would want try to respect the following two equations. So try takes two arguments, the computation it tries to run and what it does in case the first computation fails. So if I try a computation that fails, and then I resume with the handling computation M, but if the first computation returns a value, then I ignore the handling computation and just return this value. Okay, we agree on this. Now, if we also wanted to try to be an algebraic operation, we would need an equation like this. This is an equation that all algebraic operations support. So if you sequence two computations, and the first one performs an operation, you can pull that operation outside. Okay? So bringing those two things together gives us a counterexample. So let's take some computation n and bind 0 to x in it. Okay? Well, by the second equation, a computation that returns 0 is the same as trying to return 0, and if that fails, which it doesn't, return 1. Okay? And now, due to algebraicity, we can distribute this try over the monadic bind. Okay? So we get into this form. And now, if we choose n in such a way, and it's really not hard to do, so that plugging 0 into it fails, but 1 not, then this computation will fail, and we'll get this one out. So we end up that this is equal to this, which obviously doesn't hold in general. Okay? So try was out of the question, right? Not only we couldn't prove that it was algebraic, we could prove that it was not. Okay? But you could see that try was of a different nature, right? So in their original paper, John and Gordon said that, yes, only exception raising operations are definable. Exception handling isn't definable. But they also noticed that the monad they get is still the one you would expect for exceptions. Okay? And then later on, talking to Andrzej Filiński, they figure out that there is a notion of handle being a deconstructor as opposed to the constructors, which are the operations. Okay. So we have a picture like this. So we have constructors, we have deconstructors, which we cannot understand what they are. Okay? And there is this big hole in the bottom left of the table. Mathematics tells us if exceptions are just one particular example of an algebraic effect, okay, then deconstructors of exceptions must be just one particular example of deconstructors of algebraic effects. Okay? So this is the point where when I started studying in Edinburgh, and I was really interested in this question. And I tried doing some pattern matching, and I always failed, right? Because you have a choice between two computations, and you try to extract one and want to do something with it, but you could have switched them, right? And you would have gotten something else, right? We get into the same problem as before. Something with value 0 and something with value 1 should be equal, and they're not in general, okay? And I still remember when we were talking with Gordon in his office, and he had this brilliant observation that the handling for exceptions is just a model for the theory of exceptions, right? So what is the theory of exceptions? It's a single operation, fail, that doesn't satisfy any interesting equation. So it's the simplest theory you can think of. And what's the model? Well, the model is a set that provides an interpretation of every operation. So what does it mean to interpret a fail? It just means to select a point in this set. And plus the model has to satisfy the equations. And there are no equations in there. Right? So it was the simplest model you can think of. And it was so obvious that we couldn't see it. Right? And at that point, when Gordon made this observation, this is just a model of the theory. Because what is an effect handler? It gives a new meaning to the operation, which is raise. Okay? Sorry, fail. Okay? So at this moment, when Gordon said model, it all clicked together. Right? And so we soon figured out that handlers would be models of theories, and the handling construct would be the induced homomorphism from the free model. So I'm not going to go into those mathematical details here, but the important thing to point out is we, again, found something that was both unifying and existed as a mathematical notion for hundreds of years. Homomorphisms were around since the beginning of algebra. Okay? So after this, Gordon took a sabbatical in California for a year, and I went back home. And at that point, Andrzej Bauer was working on a toy project of his, which is the programming languages zoo. So it's a collection of small programming languages which express different features such as imperative programming, objective programming, typing, untyping, eager, lazy evaluation. And he said, let's try and implement those handlers of yours. Okay? And when we started doing this, we again had all the tools in front of us, and we could experiment. And we found a number of additional examples like multi-threading or search functionals and stuff like that. So we saw that we have something at our hands, and we wanted to do the same thing that Philip Wadler did for Eugenio Moggi. We wanted to do it for the handlers paper. Okay? So that's what we attempted to do. And soon, F was moved out of the PL-Zoo repository into its own repository and became a language of its own. And that was in 2010. And we made a few wrong turns when introducing F. So this is the code from the first F. Okay? And it's Python-like. I don't know for what reason. Like we fell into the same trap as most language designers do. They try to come up with the best syntax there is, and this is what it felt like at that point. Okay? So that was one mistake we did, and the other mistake we did is we published F without a type system. Okay? We knew that there was a type system. We had papers about the type system for effect handlers, but the response we got is, of course this construct is so flexible, it's untyped. And we were trying, no, it's not that flexible because it's untyped, but we couldn't convince anyone. So we immediately built the type system. But apart from all the misdirections, there is one thing that we did right, and that is the interpreter for F. Because it was just based on the mathematical definition of how handlers operate. In fact, like F has changed thousands of times. There are numerous commits. I don't know, I've forgotten exactly how the development went, like what all the versions are. But one thing that remained mostly unchanged was this interpreter. It's more or less still the same as it was 10 years ago. Okay? Okay, so, but we came to our senses, and on our trip back from a domains workshop where we presented F, we had one of the best refactoring sessions ever. So it was a train trip from Swansea to, I think, Manchester Airport. And then we decided, why are we insisting on Python syntax? OCaml syntax just fits so much better with what we are trying to do. And it was like, all the examples became shorter, things made more sense. We already had a val keyword reserved. So it was, so in addition to the type system and the syntax, F took another inspiration from OCaml, and that was how effects are done. So we wanted to be able to simulate OCaml's references, the way you can create them. Therefore, we introduced instances. So you didn't just have two operations, get and set. You declared an effect reference, which was equipped with those two operations, and then you could create multiple instances of this effect, and you could handle each one in particular. Okay, so this was the answer to the solution of the equation. Okay, we did make one mistake here. And this is the reason why Xavier was thanking me and not me and Andre today. Okay? So even though in introduction of this F paper, we said, we streamlined the paper for the benefit of the programmer, actively acknowledging that we are taking the same path that Phil Wadler took, we made one big mistake. In section 4, we gave domain theoretical semantics, and in section 6, we give examples. Okay? Section 6 should have been section 2, okay? And this is what that I've tried to correct with the introductory paper, okay? And also we didn't have operational semantics, so this was a huge wall that if I had a chance to write the paper again, I would tear down. Okay, so but what are the other differences between the numerator and the denominator here, okay? So the first thing is, we were in a programming language, we were unrestrained, so we had some extra flexibility. If you take a look at the original handlers paper, you can see that it's very syntax heavy. There's a lot of parameters lying around. And that was quickly resolved in F because we made handlers just values. So you can put them in functions, you could pass them around. Like everything ended up being much simpler. Okay? Another thing that we simplified is we added a value clause into the handlers. So originally, a handler consisted of just clauses telling you how to handle operations. And, but then in practice, we realized, because sorry, why was it like this? Because that is what mathematically models are. Models just tell you how to interpret operations. The value clause gives you the induced homomorphism. Like you tell what to do with values, and then this lifts to the homomorphism that deals with all the computations. Okay? But we saw that in examples, we never ever reuse the model. We almost always wanted to have the value clause attached together to the handler, and that's what we did. And by that, in the original paper, we had it like this. We had tried this computation with this handler, ignore the parameters, and this was the value clause as x in t prime. Okay? And because we had two concepts, models, homomorphisms, and those required two syntactic constructs, handlers and the handling mechanism. Okay? But we just merged those two into a single concept. So, and it's interesting because like we went with Gordon, we went through numerous variations of what this syntax should be like. Because there is a problem. If your handler is really big, the value clause is in the continuation. This was actually the continuation, is hidden, obscured behind this huge block of code. And Nick Benton and Andrew Kennedy had this problem first. So they were doing this for exception handlers in their exceptional syntax paper. And they suggested this notation, try x unless this goes this in t prime, but then it was not obvious that x was bound here, not in t. Okay? So there was a bunch of problems, so we went through numerous variants of this construct. Each one had their own disadvantages. Okay? But packing it all up into a single package, and just this problem that we spent hours and hours on disappeared. Okay. And another thing that disappeared were equations. So in our original paper with Gordon, we emphasized there is a natural need for two languages. Because if you want to give semantics to handlers, they have to respect the algebraic theories. Okay? If an equation holds between your operations, then a handler for those operations must respect those equations. So that's a natural need. That was our solution. A two-layer system, one language in which you write handlers, then you check they satisfy the equations, and then in the next language, you use those handlers. So I dug up some old slides from the presentation we gave at ESOP. So this was a slide. Programmer writes and uses handlers. Nonsense. Something like this should never happen. No, instead the language designer will write the handlers, and then the programmer will just use the provided handlers. I don't know, maybe the future will tell that this is a better idea, but this is definitely not where we are right now. And another slide was like, this is a handler that computes the maximum of two results. So it tries both options and then computes the maximum. So this was a handler for non-determinism, but a handler that sums up all the results was not a handler for non-determinism because it didn't respect the idempotency equation. Because if you have a computation that chooses between free and free, if you sum up all the possible results, you get 6. But choosing between free and free is just free. And in that case, if you sum up, you would get free. So that didn't work, so we prohibited handlers like this. Okay? But when I was looking at this, I was wondering what did Andre and I say about equations in the F paper. And in fact, I couldn't even find a mention of equations anywhere in the paper. We just ignored them. Okay? And another interesting thing that didn't pop up was like nowadays, if you're describing effect handlers in your language, one of the first questions is it a deep handler? Does it go into the continuation, or is it a shallow handler? Does it handle just the first occurrence? Like, this question never popped up in all the years of thinking about handlers or designing F, because deep handlers were just the natural notion, okay? And it was only afterwards in their ICFP paper, Ohad, Sam, and Nicola found this distinction that we shallow handlers may also be interested, because you can only see this when you're coming from an operational point of view. Okay. One other thing, they mention in the same paragraph that deep handlers are similar to folds on algebraic data types. In fact, they are, right? Like the concept of homomorphisms of algebraic theories has existed in computer science before handlers in terms of algebraic data types and folds over them. Okay. It was this combination, like the difference. So why are handlers different than folds? Because in handlers, the operations propagate outwards. They're alive. Whereas in algebraic data types, the trees remain as they are. That's sort of my understanding, but I still can't pinpoint the exact difference between why is handling a new construct. Okay, so that's the brief history, and now let me give you two directions. So first, let's go upwards towards mathematics. So Ohad and Gordon had another paper which was about effect-dependent optimizations. So if you have equations in your theory, like they do not only describe how effects behave, they also entail additional equations. For example, so this is again the same theory for choice, and there is the algebraicity equation for the choice, but choice satisfies multiple additional properties. For example, here are two. So the lower one is if m does not depend, if n does not depend on x and if m does not depend on y, you can exchange the order if non-deterministic choice is the only effect you're performing. You can exchange the order of operations. And another one is, it may look strange, but so algebraicity tells you if the first computation in the bind does a choice, you can pull it out. But you can also do the same for the second computation. If the second computation makes a choice, you can pull it out. You can prove this with induction, but only if there are no other effects present. But if you only have choose and fail, you can do that. Okay? And then by throwing away the equations, we also throw away those nice results, which is a shame for two reasons. First, we get weaker results. And second, we are forgetting about a nice and important mathematical concept. Okay? So Andrei and I tried to remedy this in one of our later papers on effect systems, where we also introduced the induction principle for a computation in an effect system. And what we did is we did reasoning under a handler. So if you have a particular handler, then you can still perform some manipulations on the computation underneath that handler. So we have the state handler here, and we say h of c with this initial state e. This is c handled with h and then applied to the initial state. Okay, because this gives you a function, you bind it to f and you apply it to the initial state e. And if you define h to be this, then you can recover the original equations for state. So for example, if you look up an update on the same location, that's the same as doing nothing. If you update twice, that's the same as doing the second update. If you update and then look up, that's the same as just doing the update and then substituting in the value. But previously, those are equations. Now they are equations underneath a handler, and you can compute them, and it's not hard. So for example, you can repeat this for any concrete handler. For example, the maximum handler for non-deterministic choice, with which tries both branches and takes the one with the bigger result. That one actually respects all the equations for non-determinism. And therefore, if you say h max of m is handling m with h max, then, for example, you can do h max of sequencing in this order is the same as h max of sequencing in the other order, of h max of choosing in the second computation after the sequencing is the same as h max and then pulling this choice out. And you can, and you have to repeat this for any other handler that respects those equations. So for example, the sum handler, even though it doesn't support idempotency, it still respects enough equations for those two laws to hold. But for example, for the list handler, which collects all the results in a list, it satisfies the first equation, but not the second one, because the order of the elements in the list changes. Okay, so it's a bit of a nuisance repeating the proofs over and over again. Plus, we see that it's not just the question, a handler respects the equations or not. You can see that handlers can respect certain subsets of equations. So this is the associativity equation for choice, commutativity, idempotency, so choosing between x and x is the same as x, and this is the unit laws. Okay? And different handlers respect different equations. So for example, the maximum handler, taking the biggest result, respects all of them. The sum doesn't respect idempotency. List doesn't respect, putting everything in a list doesn't respect commutativity at idempotency. And then you have those two handlers, left and right. We just take the left or the right branch. They, of course, don't respect commutativity, but surprisingly, they respect associativity and idempotency. Okay? And then there is also this swap handler, which just swaps the order in the choice. And that one also respects all the equations, and we'll come back to it later. Okay, so there is richness behind this. So the question is, what can we do with this, right? So what happened is, so I think, if I'm correct, you've talked about something of this form today. So if I have a computation type, so this is a type that returns values from the type sigma and causes effects described by phi. So in our case, that would be the set of operations it can call. Well, how do we interpret computations of this type? Well, we interpret them in the free monad or the free model for this effect with generators, so values from the interpretation of sigma. Okay? But what we were doing in F is not taking the free model. We were taking the absolutely free model. So the absolutely free model is the same as the free model, but you're not quotienting by equations. So you're just building all the possible trees. That's the absolutely free model. Whereas the free model, it's what was originally intended, was taking all those possible trees and then equating some of them. So we were quotienting by the relation generated by all the equations. Okay? So the idea was, well, here we have two components which are in the type system. Here we have three things. Why not put those equations in the type system? Okay? And so from a typing judgment like this, so a computation M returns values from sigma and performs operations described by phi, we tacked on a third thing, the equations. So in fact, we tacked on this thing before even understanding what that means. Okay? And if you think about it a little, it means, why did we do this? Because it was here. So it was obvious it must have a syntactic counterpart. So what does this mean? Computation M returns values from sigma, causes operations from phi, and we consider operations equivalent modulo those equations. So we're quotienting in a way. Okay, so those are the equations. And If we do this, we can split this previous reasoning into two parts. So first, we need to show that a handler respects a certain set of equations. So for example, the maximum handler takes a computation producing integers and then choosing or failing, and it respects all the equations, and it gives you back an integer. And it causes no further exceptions, no further operations, therefore there are no equations to satisfy. So if you have an empty set on the second place, you also have one on the third place. But then the sum, I made a mistake here. The sum doesn't satisfy the idempotency, but it gives you the same thing here. Or the list, again, the type and the effects are the same, but the equations are just associativity and the unit laws. Okay, and so why did I mention the swap handler before? The swap handler is interesting because you can assign it multiple types. If, for example, if on the right-hand side, you would consider computations equivalent only up to associativity and unit, then this handler does not respect commutativity. But if you include commutativity on the right-hand side, you're quotienting more, therefore your handler respects more equations. Okay? So you can assign it multiple effects. And there is this, multiple equations. So there is some sort of equation polymorphism going around in the background, which, as far as I know, no one has explored yet. Okay, so that's the first part. You show that a handler respects certain equations. And the handlers still have the same form as before. Before, they were going from one computation type into the other computation type, and now we just extended those computation types with the third component, and handlers still go from one computation type to another computation type. And then and what you can then say is you work on your equations in terms of some theory. And you say then, yeah, those two computations are the same if we're working modulo this theory E. Okay? And then the type system ensures that if you consider those two computations the same under those equations, and if the handler respects those equations, you can apply it on both sides and still get back the same result. Okay. So this is how the rules look like, and they're the same rules as you've seen a couple of hours ago for values, bind, and perform, except this quotient is added at the end of everything. So no big changes. Again, the rule for handling is the same. If I have a handler going from here to here, and if I have a computation M from the left-hand side, then I'm going to end up with a computation on the right-hand side of the handler. Again, the same rule. The subsumption rule is slightly different. So if I have a computation of this type, then I can safely increase the type of values. I can safely increase the effects. But there is contravariance in the equations. Because recall, this means, and we consider all those equivalent. We can always consider more things equivalent. Okay, so this is just collapsing, and we can always collapse more. Okay. And then, the complicated rule is the rule for typing handlers, as always. Okay, so and it's split into two parts. So if we have a handler going from this type to that type, which means that it has to respect those equations, the first thing we need to do is, there's sort of semi-arrow here, we need to type check all the handler clauses, which is, so this collapses all the rules that you've seen so far, like the list of typing rules for every particular clause. This is an auxiliary judgment, and once you have all the clauses, then you need to make sure that they respect the equations. So what does it mean that a handler respects equations from E? You go over all the equations T1 equals to T2 in E, and what you do is you interpret both sides of those terms underneath a handler, which just means replacing every operation with its interpretation according to the handler. And you're doing this modulo this E prime. So this E prime allows you to quotient further things. Okay? And the other rule, which is the one that you use to prove things in a given theory, is if I have something in the theory, some equation, I can always instantiate it with arbitrary computations of that type. Okay? Because recall that algebraic equations consist only of operations and variables. There is no language constructs between them. We have choose mn equals choose nm or something like this. We don't have ifs or pattern matching or functions inside them. So they're very polymorphic. And in those variables, you can then plug in arbitrary terms. Okay. So again, the first half is just checking that the handling clauses are well typed, which is what we're used to. And the new thing is this rule for respecting the equations. And this then, of course, introduces this complicates things quite significantly, because suddenly your type system depends on the logic, and your logic depends on the type system. And it's not just that. It's the type system is split into multiple judgments, one for computations, one for handlers, one for values, one for subtyping, and on and on and on. But it works. And together with my student Žiga Lukšić, we have a paper in JFP, if anyone is interested about them. And Žiga also attempted to put this into practice, so he created a fork of F called EF, F with equations. And in there, he already moved towards a practical language. So for example, the first thing that he realized is, in my effect system, I had a set of equations. No one in their sane mind would always write those equations. In fact, he already introduced a concept of theories, and there you can list all the equations, and then you can make unions of theories and so on. And then you just write toList is a handler taking computations, returning integers, and respecting the associativity of choice, and gives you back an integer list and no effects. Okay, so this is, like, if anyone's interested, this is up for grabs. So right now, the language, of course, doesn't do any checking of the equations. It just prints them out. But you can imagine putting this into an SMT solver, or doing some sort of a quick check, or generating proof obligations for your favorite theorem prover or something like this. Okay, but so one main takeaway from all of this is there were absolutely no issues in this development. When we started writing the paper down, there were no surprises. Everything just worked as expected from the very beginning, because it had solid underpinnings. The other story is a bit more rocky, okay? So in 2015, I visited Tom Schrevers in Leuven, and our idea was, we have F, let's try to make it execute efficiently, okay? So that was our goal, because we knew that handlers were flexible, but were they efficient? And this was still before OCaml, of course, supported handlers natively. So, but still, we knew that the most direct way to get to efficient execution was through OCaml, because OCaml already had very efficient execution, so we only needed to translate F into OCaml, and it seemed pretty straightforward, because like the languages shared 95% of their features. Okay. So what was the idea? Since OCaml didn't have handlers at that point, is we would do a monadic embedding. So we would define a free monad. So this is just an example of a monad for state. So we have a get and set operation. So we define type alpha comp, which represents computations returning values of type alpha, and they can return them, or no, they can perform a get, or they can perform a set and then have a continuation here. And again, and we would define a handler with a number of clauses, which I'm omitting here. And from this, you can define the standard operations like return and bind and map and get and set and handle. Okay? So one thing that caused us problems later on is we needed this handler not to map into an arbitrary OCaml type, but into a type of computations, because a handler may not handle all the operations in this first computation, and those have to be carried forwards. Therefore, this also had to be a computation type. Okay. And our strategy for translating into OCaml efficiently had two parts. So the first part was purity-aware translation. So we wanted to avoid monads if possible. So here is an example of a program in F. So it reads something, it increments the location. It reads it, stores it into Y, and then stores Y plus 1 into it and loops again. Okay? And what we wanted is to get something like this, a bind here, and the two operations there. That made sense. What we ended up was a number of binds, because everything was a computation in F, and therefore everything had to be sequenced, and all those sequences transformed into binds, and that was horribly inefficient, working with the free monad everywhere. So what we wanted instead was do the binds only where necessary, and do usual lets, and pass around usual values where we were sure that the computation was pure. And it was an obvious idea, right? How do we translate a computation type sigma causing effects in phi? Well, we just translate it into, we just translate sigma if there are no effects, and if there are some effects, then we translate it into the monadic embedding. So the computations returning values over whatever sigma represents. That seemed obvious enough, but we had numbers of problems. Okay? And I'm not going to list all the special cases we had to do in this translation. But so another computation, another optimizations we did was inlining handlers. So here is again this simple loop program and the handler for state. And what we want to do is, if we apply this state handler to this function, what do we get? Well, so if we have something like this, right, we can see that we have a with handling an if. Okay? So what we want to do is we want to push the handler inward so it reaches the operation. So we put it inside the with. Okay? And then at the next step, we have a with applied to either values or computations, and we push this handler even further down. Okay? And we end up with something like this. But then we encounter a problem, because we have a state handler applied to a function. We cannot go inside a function. Well, we can go. So what we do is we do a little bit of specialization and fusion. So each time we apply a known handler to a known function, so we need to have both sources available, okay? We define an auxiliary function, loop prime, which is the state handler applied to the original function. Okay? So what do we do with this? Well, then we can unfold the body of this loop function. We have the state handler here. We do the same thing as before. We push it. We push the handler through the body until it encounters the loop. Okay? And now we know what to do with this, because this is how we define loop prime. So we ended up removing all the operations and all the handlers from the code. Okay, so that was the idea. And we got really promising results. Like combining both approaches, we got the same code that ran as fast as handwritten OCaml code, but with all the modularity that handlers provide. And we also submitted a paper to ICFP, and then it all collapsed, right? Because well, the reviewers complained there weren't enough benchmarks. But why there weren't enough benchmarks? Because as soon as we tried to make one benchmark work, the other one failed. Because the effect system implementation we had was based on implicit effect information. And it was really hard to wrangle. And there was numerous bugs. And every time we solved one bug, we opened 2 more bugs. So we made one attempt to get rid of those instances and moved to global effects, but that didn't help either. Okay, so the story had to be reset. So how did we in the end get from F to OCaml? So first, what we needed to do is we had to annotate every subtyping occurrence with an explicit coercion. So we were tracking all those coercions. And then what we did is we created a small language very similar to OCaml, which we called NoF, which is a functional language, but with a separate type for computations. So the same as a monadic embedding. And then later on, we did this translation from now having the explicit information available, it was much easier to create all the coercions. And after that, we did all those optimizations at Uppsala a couple of years ago, and those then worked flawlessly, and we got the same results. Okay, so, but there were still a few more surprises waiting. Okay, so how did we translate things? How do the coercions look like? So we have simple coercions like for every type, we have the reflexivity coercion going from sigma to sigma. Then because of polymorphism, we can have coercion parameters omega. And then if we have a coercion going from sigma prime to sigma and from tau to tau prime, we can create a coercion on function types, which applies this coercion on values, then applies the original. So if I have a function from sigma to tau, there should be a prime here. How do I get a function from sigma prime to tau prime? Well, first I take the sigma prime, I transform it using this coercion into a sigma, then I apply the original function, I get something in tau, and then I coerce this into tau prime and I get back a function from sigma prime to tau prime. So that's one thing. And for computations, we can increase the types of values and the effects, both explicitly. And how does this translation then work into OCaml? All those coercions need to be translated into functions, because now in OCaml, there is a difference whether we have a pure computation or an impure computation. The types have to match. And like the reflexivity coercion gets mapped into the identity, the coercion on function types goes through what I've described here. And the coercion on computation types, okay, so if this is a coercion mapping one computation type into the other, what do I do? Well, if both types are pure, then I'm working with values on both sides, and I can just apply the coercion on values. If the first type is pure, but the second one is impure, I coerce the value, and then I have to insert it into the monad. But if both are impure, both were monads before, so we can just map on the free monad. Okay, and then we run into problems. So this is a simple program in F. I have a polymorphic function that applies F to 0, and I want to apply this function to cosinus. To cosine, which is from float to float. Let's say that I have some coercion going from int to float. Okay? So internally, we annotate all this with types. So apply 0 is polymorphic over the type alpha, over the type beta, and the result, the argument of F doesn't have to be an integer. It can be larger than an integer. It can be, for example, a float. So what I need to do then is provide a coercion going from integer to alpha and then apply the alpha. So I take 0 and I coerce it with this argument omega, and only then I apply F. So if I want to apply 0 to cosine, what I did here is I need to instantiate both alpha and beta, and then I need to provide an explicit witness for this coercion, something that maps integers into floats. Okay? And when I translate this into a camel, this omega has to be passed in at runtime. So there's this argument W. Okay? And you could say that it's just a single argument. Well, our effect inference algorithm is really happy with producing those coercions. So the standard library has 450 coercion parameters, and the quicksort function has 200 additional coercion parameters, right? So this is, so altogether it has 201 arguments, right? 200 coercion parameters and one list that it sorts, okay? So we want to get rid of this, okay? And our first idea was garbage collection from Francois, but yeah. And unfortunately, it does not work, because there you could throw away the constraints, but here we have coercions which appear in the terms and they have computational content, and we can't just throw them away. Okay? So we are resorting to some heuristics with my other PhD student, Filip Koprivec, and the main result that we have right now is we have a bunch of simplification algorithms. And if we have a polymorphic function, okay, and if we have some instantiation of this polymorphic function, then there always exists an instantiation of the simplified version, so sigma v. So we find a substitution that collapses a lot of those arguments. We find an instantiation for the substituted term. We don't get the same thing, but there is always a coercion mapping between two, and those two terms have the same denotational meaning. So we can simplify things. So how do we do? Like before, you can imagine all those to be all those coercions in form of a graph, and in this graph you can collapse the loops. And the next thing you can do is you can collapse the strongly connected components, because if this type is less than this, less than this, less than this, less than this, they all have to be equal. So you can collapse them, and then further on you can collapse types that don't have any impact on the outside type. And in the end we can get rid of not all the situations, not all the cases, but in practice, before, we had 447 type coercions, which means 447 additional parameters in the standard library. At the end, we have none. Okay. So that's the other path downwards. It was full of surprises and troubles. So maybe just to end, the path forward, okay, moving away from handlers. One recent thing that Ohad discovered when he was trying to solve advent of code, he had a problem where there was a lot of symmetry in there, and he was doing it in Idris, so it was a huge suffering to do all 100 cases by hand. So symmetry is one thing that occurs in computer science, but is really underused. So for example, when we are teaching self-balancing trees, you always consider the case when I rebalance the tree, if the right one is too heavy or if the left one is too heavy. And for the left one, we always say, without loss of generality, it's symmetric to the first one. But if you're doing this in a theorem prover, you have to repeat your proof. So there is a lot of nice mathematics behind this. So it's group actions and symmetries, but there's still so there's definitely something there, but we still need to translate it into a useful concept. So yeah, thank you.